Hi, everyone. Welcome back. It's time for our next talk from Karin Erdmann, the Nakano Theorem and relative dominant dimension.
Can you hear me? Yeah. Okay. Great. Thank you. Thank you, Dan, for inviting me, and yes, actually, thank you for existence, right? So, so this is a picture. So I can look into this one here, right? So this was in MSI in 1990. So there were two workshops, and one of them, Dan was there, and I was there as well. Not sure where I am in this picture, but somewhere, maybe in the middle there, just next to. Oh, I don't know. Dan is somewhere at the front, somewhere here. No, not this one here. Yeah. And I think I'm here. Can you actually see if I point to this thing? Okay. I was actually rather desperate because at home I knew I had this photo, but I couldn't find it. And so I gave up eventually. And but fortunately, Dan has the photo amongst these 354 pictures, right? Yeah, so. Anyway, but I do have another photo, which I don't think Dan actually has, so I should show you. Yes, do you have this photo? Oh, you have that as well. Anyway, so I like this photo because there's also Dave Hemme on here, and John Carlson is on here, and well, of course Dan here, and me. But I was a bit worried because Dave was at this conference, but he is not on this photo. I don't know what he did. So this was in Oberwolfach, and it was a mini workshop on support varieties in 2008. Yeah. Right. Okay. It's not a good picture. I've done it with my mobile, and my technology is not terribly good, so I apologize for that. Anyway, so here is the motivation for what I'm talking about. And yeah, sorry, I should go back. Say one more thing. Maybe actually go back to this one here, because it's sort of historical. So when I was there in 1990, I just more or less decided, well, it's about time to leave the tame blocks alone and do something different, right? And so there was just the time when highest weight theory and quasi-arbitrary algebras came up. And I thought, okay, right, so we have Schur algebras, and well, I know how to compute equivalence and relations, so why don't I classify Schur algebras of finite representation type? And so then, well, that's good because Dan was interested in Schur algebras, and some other people as well. So Steve Doty was there as well, I believe. Anyway, so then we looked at representation type of Schur algebras in general, and Stuart Martin is also in this team. And then, of course, then the question is what happens with q-Schur algebras. And so Dan and I classified q-Schur algebras of representation type of q-Schur algebras and also of Hecke algebras, because that's close together. So this is the only time that we had I know that I had a referee report where the referee said, well, why don't you make two papers out of it? So I don't know, maybe the referee was here, but thank you. All right, so this was the joint work with Dan at that time, but I suppose later we got on, there was this meeting in Cambridge for which I don't have a photo, but at that time we discussed cohomology basically. So question is, how can you relate cohomology of GLN or Schur algebras with that of symmetric groups and get some information out from symmetric groups or Hecke algebras? So Dan had the great idea to look at spectral sequences. So I really like that. So we have this paper with Dan and Steve and about spectral sequences and how you can use that for symmetric groups. Anyway, so there were some more papers by Dunn and co-authors on the same question. So I mean, this is really very important because quasi-hereditary algebras or GLN, they have nice homological properties. So you have nice X vanishing, and simple modules don't have self-extensions and some other things, finite global dimension. But for symmetric groups and Hecke algebras, this is very different. On the other hand, you have the shadow of quasi-hereditary. For example, if you look at Specht modules, you know that there is some ordering on the composition factors, so there could be some connection with highest rate theory. Anyway, so here is the, yeah, sorry. I should just say that, I mean, I once, not long ago, gave a lecture without writing it. I was far too fast. So now I'm trying to slow myself down. But I won't overdo it because, yeah, right. Okay, right. So, okay, so here is the question. So if you have modules with Weyl filtration or dual Weyl filtration of pure algebras or highest rate categories, then one knows that filtration multiplicities are well defined. And on the other hand, if you look at symmetric groups, this is obviously not true, because if you take prime 2, then you know the trivial module is a Specht module and it's isomorphic to the alternating module, and so you can't have uniqueness of filtration multiplicities. And similarly, for p equals 3, you have examples. I hope I got this one right here. So this is the sign representation, and this is a simple module, and this Specht module 3.2 has 2 composition factors, so you also have not uniqueness. However, the theorem, Nakano Theorem, says that if the prime is at least 5, or for Hecke algebras, L is at least 4, then modules with dual Specht filtration have well-defined multiplicities. And well, this was a surprise, actually. At the time when I heard about it, I was talking to Gordon James, and I remember that that's the only time ever that I've seen Gordon James to be surprised. And he seemed to know everything, but this one he didn't. So anyway, but, okay. Right. Anyway, so the paper has ingredients from the previous paper I mentioned, so work by Keshev, Nakano, Doty, this paper with the spectral sequences, and also some papers by Doty, Nakano, and probably some more. And it has some more results in this paper. One is some comparison of X. So you have a module with good filtration, Weyl filtration, and you take X in for the Schur algebra, then if the index is not too big compared with P, then you got isomorphism between the X and the symmetric groups. And then, so that's one result. I mean, similar things more. And then there's also a new construction of Young modules. And okay, so this is very nice. And I added the last bit on this page just to illustrate that there are open problems which you can't answer by this approach. At least we don't know whether you can answer. One is the question is whether simples for Hecke algebras or symmetric groups have self-extensions. And I think this is an open problem. And I think the tools here, yeah, I mean, there are partial results, but this is open, right? So anyway, so what I wanted to talk about is how this has actually had impact on representation theory of algebras. And I think this is rather good. I mean, on one hand, you have impact from representation theory of algebras to algebra theory. And this is the thing that tilting modules came into the game. And so you can also go the other direction. And the question is, what results from Lie theory actually have some impact in representation theory of algebras? Anyway, so here is the Nakano Theorem. So Fang and König have written some paper, which, sorry, I haven't, I should have given you the title, and I haven't, but you find it on, you must sign it or whatever. Anyway, so they view the setting via dominant dimension of an algebra, and they say, okay, with the dominant dimension, okay, so what is the dominant dimension of an algebra? So you take the minimal injective resolution of the algebra, and so you ask when the terms, which terms, whether the early terms are projective or not, and the dominant dimension is the smallest n, so that the first n terms of the injective resolution are projective. So, for example, if your algebra is self-injective, then this would be, would be infinite. But in general, it's not. Anyway, so they have some theory about dominant dimension, and then they can use it to relate an algebra in A and an idempotent algebra, and the results apply to Schur algebras and some other algebras. And so they're interested in this X condition. So I had on the previous, yes, right. So that's why I wrote this down here. This comparing X between the Schur algebra and symmetric group, and they do this for algebra. So they compare X with A and B, and then they introduce something they call the Nakano dimension, which I'll be explaining in detail in a minute. Okay, so that's all very nice, but it works for Schur algebras when n is greater equal to d, but it does not work for Schur algebras when n is smaller than d. And yes, right. But there's no also very nice account of that approach, which works really well and is very general. So you can also attack the setting for Schur algebras with any n and d, or more generally, if you look at quasi-hereditary covers, but you don't use the Schur algebra or the quasi-hereditary algebra, but you use the Ringel dual of this algebra. And yes, and then you can characterize or compute Nakano dimension in a different way. And I should say something about, before I forget it, why I got into that. So there was this lockdown, and because everybody is miserable and sits at home and asks, what can I actually do? Yeah? And and so at that time, Steffen sent me an email, would you have time to examine the PhD thesis of my students? So this is Cruz. So this was 21. And well, I was very happy because I had nothing to do. So, and the thesis had actually 400 pages. So it was quite a challenge. But anyway, so yes, I said yes, very good. And so then he had some examples in it. So we computed this dimension for S24 in characteristic 2. And so I got hooked on that because, well, I can do that as well. And so I thought maybe I can also do 6 or 8 or whatever. And so, yeah, so anyway, so I worked on that, and this was really good because it saved my life during the lockdown. But unfortunately, what I did was wrong. Anyway, so at some stage after the lockdown, we had a chance to meet and talk about it. And so then, of course, I noticed that what I was doing was wrong. And so he had a better idea what we could do. And so we did that. And so that's what I'm talking about. And now we have a theorem which is correct, and it's actually in the meantime published. So. All right, so here's the setting. So you take a quasi-hereditary algebra, and so it's the highest weight theory with respect to some whole set ordering the simple modules. So you have simple and projective modules. So how long am I supposed to talk?
1205.
12 or 5? Okay, at most, but, okay, right. So, okay, so we have simple and projective modules, and they're labeled by lambda in this index set. Then there are standard modules, so this is the quotient of, biggest quotient of the projective, where all composition factors are less or equal to lambda. And then you can look at the modules which have filtration by standard modules. And then you also have dual versions, so co-standard modules, the largest submodule of the injective with composition factors at most lambda. And so they have filtrations, and you have this category of modules. So the interesting thing is that the intersection of these two subcategories, so which is the modules with both filtration by standard modules and co-standard modules. This is, wow, I mean, this is the additive category of one module, and the number of indecomposables is the same as lambda, and the indecomposables are parameterized by highest weight, and the highest weight is again is lambda here. And well, this was originally done in some algebraic setting, and then I suppose Steve Duncan noticed that this was actually very interesting for algebraic theory, and so he wrote some paper, and this has taken the subject into theory. Anyway, so then this module is now called characteristic tilting module, and I suppose one is a bit sloppy in theory, just talked about tilting modules and also about some ends of that tilting module. But in principle, I mean, if you be precise, you should be calling it characteristic tilting module. Anyway, so the endomorphism algebra of this module is again quasi-hereditary, and the order is the opposite order of lambda, and then if you do that twice, you come back to the algebra A up to Morita equivalence. So it's called a Ringel dual, and Ringel was responsible for this discovery. So anyway, so if the algebra has a duality which fixes the simple modules, then the standard modules and co-standard modules are just the duals to each other, and the tilting modules are self-dual. And so for sure, algebra, this dual is the contravariant dual. And it's interesting, it's a duality on the module category rather than from the module category to its opposite. And yes, right. And for sure algebras, the standard modules are the Y modules, and co-standard modules, sometimes called induced modules, and the tilting modules can be constructed as a direct summand of generalized exterior powers. So it's all in some sense very explicit, but it's difficult to compute these things. Right, so okay, so Uke has introduced quasi-hereditary cover, but I learned yesterday that it's known as highest weight cover. Somebody called it highest weight cover. Right, and yes, so okay, so you have an algebra and a projective, a quasi-hereditary algebra. I see there's a typo, there's a P missing. So there's a projective module P, and this endomorphism algebra is B. And then this is a quasi-hereditary cover of B if you have double centralizing between the image of A and B. If F is on A, P blank, which yes, right. So this is you can even in general call this a Schur factor, even if it's not the usual Schur factor. So the typical example is the Schur algebra, and n greater or equal to d, and V is the group algebra of SD, and the P, you take the yes, you take the d tensor power of the natural module of GLN, so V is n-dimensional, And this is a projective module for the Schur algebra. And the idempotent you can take is the, in the green notation, psi 1 to the d, for example. And the Schur functor, you can think of that as Hom A E blank, or you can also think of that as E just multiplying by E. It's the usual Schur functor. So this a nice functor, is exact and has a left adjoint, it also has a right adjoint, and yes, and this is behind the scenes a lot. And anyway, so the Schur functor takes the dual, the standard modules to the dual Specht module and the co-standard modules to Specht modules. And so it is exact, and therefore it takes the category of modules with delta filtration to the category of modules with Specht, dual Specht filtration, and it takes the modules with co-standard filtration to the category of modules with Specht filtration. And you can also say what the tilting modules are taken to. You get the signed Young modules for the conjugate partition. And anyway, so then how can you say wrong? Right. Okay, so now we come back to the Ext, comparing Ext. So you take, maybe now we are general, so we take quasi-hereditary cover, and B is the endomorphism algebra of this projective. And we would like that this Schur functor, which I haven't written down here, induces isomorphisms on Ext. So you ask for when do you have xj, xy isomorphic to xj, fx, fy, and you'd like to have j as large as possible. And so Fang and König have, that's what they call the Nakano dimension. So it's the largest R, so that this condition holds on for 0 less than j less than R. And yes, coming back to this slide with the Nakano, there was this case when, yes, maybe I can go back to this one. Yeah, here. So here there is some instance here. So this would actually see that in this case, this Nakano dimension is at least p minus 2. So this would be showing. But I suppose it's not really clear whether this would be the largest possible. Okay, right. Right, so, okay, so why is this interesting? So if this dimension is at least 1, then we would already know that filtration multiplicities are well defined. And this, you can see that in a few lines, because if you look at the category of modules with delta filtration, you have in this category deltas, you also have the t's, and you can show that Ext of delta and t is always 0 because t is also in nabla, right? So this is always 0. And so if you have this thing, then you can, I mean, this is the general principle. If you have X vanishing, and so you have a class of modules which have sufficiently many homomorphisms, then you can compute filtration multiplicities using homomorphisms between the deltas and the t. So I mean, this is an exercise. So you have a matrix which is upper triangular. If you just write down the dimensions of homs from the individual deltas to t's, then you get an upper triangular matrix, and so you can invert it, and so upper triangular, and then you can compute filtration multiplicities. Right, so if you actually then know that the f Schur functor preserves X, then you can just transport the whole condition to the category of modules with F delta filtration, and then you have filtration multiplicities are well defined. So if you read the Nakano paper, actually this is what is behind the scenes. Right. So then the question is, okay, so this is now more general, and this is where I get really excited. So how do you actually find this dimension in general? And this is actually rather difficult. Yeah, I mean, Fang and König done something for n which applies to n greater or equal to d. It also applies to category O or some other settings. So they have a theorem. So you take a quasi-hereditary algebra, which has a duality which fixes simple modules. And if the dominant dimension is at least 2, then okay, so then they show that the dominant dimension is twice the dominant dimension of T. You can also define that, and then they have this formula for the Hemmer-Nakano dimension of A. So you need the dominant dimension of T. T is this tilting module, and it should be bigger than 2, and you subtract 2. And right, and so then question is, what are these dominant dimensions then? And they also show that if you take the Schur algebra, n greater or equal to d, then the dominant dimension of A is always 2 times p minus 1, and the Q analog would be, yeah, what is it? 2 times L minus 1. Yes, by the way, I looked up how do you spell analog, and yes, people said, well, in American spelling is analogs with, as I did it, and the English spelling is you have analog with UE at the end. So here I'm in the US, so I spelled it this time. Okay, right. Okay, so now if you plug these things in and see what you get, the Hemmer-Nakano dimension should be dominant dimension of T minus 2. So you have to get from A to T, you have to divide by 2. So you have p minus 1, and then you subtract a 2, and so that you get out that the Hemmer-Nakano dimension for the Schur algebra would be p minus 3 or L minus 3, depending on. And of course, you want this to be a number greater or equal to 0, and so therefore, if L is at least 4 or p is at least 5, then the filtration multiplicity is well defined. So this would come out as well from that. Okay, good. Right. Anyway, so this uses that the tensor power is projective injective for the Schur algebra S and D, but this is not true if n is smaller than d. So this method would not be usable for example, S2D. But you still have double centralizing between the Schur algebras and the quotient of the symmetric group depending on Hecke algebra. And so it's not really completely out of question. And so what this Thiago did is he studied relative, not the dominant dimension, but some relative version of that. And so this is a relative version with respect to some module. And so that's what I'm going to talk about now. Right, so what is this dominant dimension? So you take some fixed module, and so then everything in a module has a approximation. So you can show that you have a map from X to something which is in odd Q, and so every theta from X to Q factors through alpha X. Or in other words, the map is exact under the functor Horn-Blanc Q. And so you can iterate that, and so you can define a relative dominant dimension, the largest n, so that you have an exact sequence where the terms are direct summons of direct sums of powers, summons of Q, and they should be exact under Horn-Blanc Q. And well, it could of course be 0 if your approximation is not 1-to-1 because you can't get started. And if you can go on forever, then of course it will be infinite. And yes, I should say that if Q happens to be the direct sum of all injective modules, then you get precisely the dominant dimension. So this is a special case. Right, so what can you do with that? Yes, I was going to do an example. Yes, Dave had one example, right? The Crotonian acting on, which I can do. So yeah, so here's an example which I can do, yeah. Right, so you take the Schur algebra S24, characteristic 2, and the module is just the tensor power V tensor 4, and V is the two-dimensional module. So it's not difficult to see that the indecomposable direct summands of that are T2 and T4. Incidentally, my labeling is, I said that at the bottom here, so you can always replace partitions by the difference because you basically can work with SO2, it makes sense. Right, okay, so you can compute this dimension. So we wanted to look at T0, which is the trivial module. And yes, right. So we can embed it into T2 because T2 has length 3, so it's 0, 2, and 0. Right, and so the quotient is, co-kernel is the nabla of 2. And so you can show that this is an approximation. It's also minimal, you can't do better. Anyway, so then the question is, how do you carry on? So you say, yes, of course, we know T4 has a submodule nabla 2, and the quotient is nabla 4. And this looks very nice. And not sure, however, this is not an approximation because we've got another map. We have a map from nabla 2 into T2, just top onto Socko. And this can show that this does not factor through this map here. So this won't be an approximation. So you have to add something. And then you take the direct sum and compute what the quotient is. So this looks like that. And then you have an exact sequence. And this, you can show that this is a minimal approximation. But then you can also see that you have to stop because the co-kernel happens to be injective, but it's not a direct summand of the tensor power. And so you cannot have an injective map from this quotient into Q, and so it's the end of it. And so you have one, so you had one term here, this was a T of 2, the next term is T4 plus T2, and then it stops. So the relative dominant dimension is 2. Right. So yeah, incidentally, this is what I did during lockdown, and because that's going on because it's far too complicated. And maybe I think I got up to 10 or so, but then it stopped. Anyway, so yeah, you have to do something better. And so Tiago had in his thesis this general theorem which describes the Hemmer-Nakano dimension. Incidentally, he works with the dual version, co-dominant dimension, because to get around the problem that this tensor power is not projective, injective. But it doesn't matter because we can dualize it. And anyway, so his theorem says that you take some summand of some module in add T, and you take its endomorphism algebra, and then the home TQ is a projective module for the Ringel dual. So this is RA is the endomorphism algebra of T. So you have a quasi-hereditary algebra here, the Ringel dual, and you have a projective module for that. P is from TQ, which is good. And so then you have the setting you need for a quasi-hereditary cover. And yes, right, so if this q-dominant dimension, a codominant dimension, is not too small, then you have a quasi-hereditary cover, and the Hemmer-Nakano dimension is greater or equal to n minus 2. So this is a very nice theorem. and you can use it for Schur algebras S, N, D, and Q to be the tensor power. And yes, here I have to say why I feel rather embarrassed about it, because in '94 I looked at Hom. So I looked at the functor Hom, the V tensor D blank, and well, it's clear that it's not as good as the Schur functor. But so what I did is I said, okay, I add something so that I get a full tilting module. Then the endomorphism algebra is the Ringel dual, Morita equivalence to that. And then my tensor space is, well, it's you apply a projection and you get this by a projection from T. And therefore, this functor Hom V tensor D is, yeah, so you take the idempotent truncation and first you take the Hom T blank, which is the functor which Ringel used, but then you truncate it, and then this identifies the quotient of S and K S D with the idempotent algebra of the Ringel dual, and you get some information out of it, which looks nice, but of course I didn't make any attempt to relate X, so feel embarrassed about it. But of course, this is now done by Thiago's theorem. So, of course, that explains also why I was interested in that. Okay, so we apply this theorem for Schur algebras NE, N, and B, and take Q to be the tensor power V tensor D. Then there is always a duality fixing symbols, and then the co-dominant dimension is also the dominant dimension. And so if you just look at A being S2D, then the algebra B you get out of it happens to be the Temple-Leaf algebra. So yeah. And so what we do is, what I was interested in doing is computing the relative dominant dimension of T in this case. And so I suppose I have 10 minutes, but well, I can always stop when I'm tired and you don't want to see all details. And anyway, so anyway, the first thing I should say, the method to compute this relative dominant dimension in the example is obviously not practicable, so we needed something more general, and so we have this theorem. So we take any quasi-Hideki algebra which has this duality fixing simple modules. So we take anything in T, then the relative dominant dimension of A is always twice the relative dominant dimension of T. Incidentally, this is what Cruz and Fang have in their case as well, but of course they have different methods. And actually this implies also the König and Fang thing again. Right, so this says, okay, if I want to know the relative dominant dimension of T, and I can't do that because it is too complicated, then instead I can try to compute the relative dominant dimension of A, and this might be easier. And in fact, it is. So we're looking at A equals S2D. So as I said, this side is rather difficult as the example illustrated. So let's look at the relative dominant dimension of A. And so what we do is that this is either in D, the same D as here, if the characteristic is 2 and D is even, but otherwise it's infinite. And there's also a Q analog. So if Q is something like that, then we get the same answer, and but P is replace P equals 2, characteristic 2, by Q equals -1. So it's the same answer. Yeah. So yes, right. So the rest of the time I wanted to explain how you prove that, and perhaps also you see that why it might be difficult to do this in general. Right. Okay. So we have okay. So one fact which I haven't mentioned. So we take an n-dimensional vector space and we have a field of characteristic P. Then, yeah, what are the summations of V tensor D? So there are tilting modules and you get only the T lambda where the partition lambda is P regular. And you can reformulate it in injectives, but anyway, so that's coming out. So this tells you that if n for n is 2 and P is not 2, then all partitions are P regular because you cannot have P equal parts. And when P is 2, then and D is odd, then also all partitions are 2 regular. But for D even, you have the partition well, SS or 0, whatever, which is the only partition which is not P regular. And but anyway, in the case, so we in any case do get half of this theorem. So if this we get this else thing. So if all partitions are P regular, then the V tensor D is a 4 tilting module, and so everything is infinite in that case. Right. So the interesting thing is when P is 2 and D is even. And so, yes, and we wanted to compute the relative dominant dimension of the algebra, and the projective, which is always there, is delta D. So this is the largest projective. So we should start by computing that. And this is actually not so difficult. And so the answer is that the relative dominant dimension is always S, so here's the half coming in, and plus the relative dominant dimension of T0, which is incidentally the same as delta 0. And this goes on to the next slide. Okay, so the main ingredient is twisted tensor products. So you can show if you take some module with delta filtration and you look at the twisted tensor product T of 2 tensor X twisted, then this always has infinite relative dominant dimension. And you can actually, this is quite easy, it's by induction, but I don't have time to do that and you don't want to know anyway. So exercise, yeah. Right, anyway, so once you know that, then you can do this proposition. And I think after I've done this proposition, I'll probably stop. Anyway, so you have delta D and you wanted, D is 2S and you wanted here the S and then you wanted T0. And yes, so there is an exact, always an exact sequence. You have delta 2t plus 2, then you have in the middle t of 2 tensor delta t twisted, and on the other end you have delta 2t. Right. So by the lemma, the middle is has infinite dimension, and this is almost what you do when you compute global dimension or whatever. So if you've got a sequence with a projective in the middle, then the n terms it goes down, and here it's the same. And so you just have to convince yourself it's exact under the Hom functor, and the middle has infinite dominant dimension, and then it goes down by, well, basically down by 1. So this tells you that the dominant dimension of the left-hand side is 1 more than the dominant dimension of the right-hand side, and you take induction and you end up with 0. And so this would prove the proposition. Yeah. So what you do, and then you have some more projective modules. It's not just delta D, you have other ones. And yeah, I mean, some work by Anna Henke and myself and Stacy Law and myself, we have looked at the Schur was S2D well, a lot, and we have a lot of technical things, and so we can prove this one here is a reduction theorem. So if the dominant dimension of the projective is either infinite or it's the same as that of delta D, and of course then you can't get any further, and then you get the get the theorem. So you can just use the lemma to do the first. Okay, so the lemma, the first reduction, and then you use the proposition, you write it like that. Then you use theorem A, and theorem A says that V tensor D dominant dimension of T0 is half of the dimension of A. And so you have an identity. Dimension of A is D half plus a half dimension of A. And now you bring one term to the other side, and then you get the answer. Right. Okay, right. So then this gives the answer. And I should just say something about conclusion, because maybe you can put up with another minute of mine. So one is, if the dimension is infinite, then the algebra is Morita equivalent to the Ringel dual and is quasi-hereditary. And we've said if the dimension is at least one, then filtration multiplicities are well defined. And so now we use this for just for the category of modules with Specht filtration, where the partitions occurring have at most two parts. And then you get a little bit more, because when you take p equals 2, then this dimension is d half minus 2, and this is greater or equal to 1 for d at least 6. So you do get some partial filtration multiplicities well defined, which is perhaps interesting. And yeah, what can we say? And if n is bigger than 2, this is difficult. So we computed some examples using the results from the UGA webpage about pure algebra. So should say that this is very helpful. And well, it's in progress, so maybe we can't actually compute it in general, but maybe what we should be doing is looking for a categorification. Thank you. Okay, that's all I wanted to say. And I don't have the slide saying happy birthday, because I have already said it.
Any questions?
I start with an algebra A, or whatever you want to call it, and I take the Reed product of the symmetric group. And I could take B now to be column vectors with entries from A,
Yeah.
and the product and
Yeah.
action on that.
Yeah.
So these are generalized Schur algebras.
Yeah.
How much of these sorts of techniques would apply in bringing in the A?
It's a very good question, and it's very interesting. I mean, the from 43 products, I think this would be a rather interesting thing to look at. Yeah, yeah. But I haven't got this one.
Do you think there's more general results where you restrict the number of parts in the partition and you get sort of more isomorphisms and homology between symmetric and Schur algebra side?
So okay, so you just look at all partitions with at most 3 parts or at most 4 parts. Yeah, I mean, this would all apply. You would look at Schur algebras as 3D or as 4D, and the question is, what is the Nakano dimension in that case? So you would want at least one. Yeah, yeah. Actually, that bit is probably not so difficult to prove, but the exact dimension is difficult.
But it's coming in bigger than P minus 3.
Yeah, maybe it's already in your paper. Is that what you're saying?
Not for that much in B.
Yeah, yeah, yeah.